Alright, so we're back with fluid mechanics. This is class 10, the first video, and we're going to take a look at Bernoulli and energy equations. This is a continuation, I believe, of, what are these? This is chapter 5? I believe this is chapter 5. Let's take a look at the book. Let's see. Yeah, I think we're in chapter 5. Yeah, chapter 4 is kinematics, so chapter 5 we're continuing on. Sure. I couldn't recall. Yeah, the name of the chapter 5 is Bernoulli and energy equations, so that's chapter 5. Here you go, is what it in vapes, and what we're seeing here is something we call a free jet, where in this case, the free jet is shooting straight up. And we can actually use this as sort of an indicator of the amount of flow. When we use Bernoulli in conjunction with the continuity equation, the incompressible continuity equation, we're able to use that sort of as a flow meter, so that's an interesting application. We can also use Bernoulli and the continuity equation to estimate the amount of flow in a siphon. So that's a good application of Bernoulli. All right, so here is a free jet. And previously in another video, we used a derived equation when we were doing control volumes, and we were using Reynolds transport theorem to show how the height can be estimated, that the rate of the height change within a tank moving. And we used something called the Torricelli's equation. So let's take a look at where that came from. So I think it's the best idea when approaching any of these problems to actually go back to first principles as opposed to memorizing the results of an equation. So the first principles, maybe. I guess I wouldn't say it was first principles. I think we should go to the Bernoulli equation and then work it through as opposed to memorizing this. But it's notable that this is a form, what we end up with, that's very common for many of the Bernoulli problems that we'll see. So we want to try to find what the velocity of the output of this is going to be in this tank. So we make certain assumptions here. Well, first off, let's write out this Bernoulli. I'm going to go from point 1 to point 2, and we'll see what the significance of that is in a second. So we're using what I call Bernoulli 1 and gamma Z1, right? There's point 1, and then for point 2, we have P2 plus 1/2 rho V2 squared plus gamma Z2. And then we like to start crossing things out. Now, first off, point 1 is obviously going to be at the atmospheric pressure. And if this thing is large enough, like we don't know the width, right? They don't even show the width. So maybe this thing is really, really, really wide. So the depth isn't really going to change. Or if it does change, it's going to be very, very small velocity. So we go ahead and we say the velocity at 1 is also going to be 0. The height of 1, well, we know that as h, so we could just replace that with h right here. And we're going to treat 2 right here as the datum. Right, so here's going to be the datum, the reference by which we go here. So that right there is going to be 0. Now we have a couple questions here. This one we already have written down here as that P2 is going to be atmospheric pressure. Well, if you go into this little zoom in thing here and you take a look at, like along here, they have to be the same pressure, right? There's no reason for it to be different horizontally. And so there's like not really a pressure gradient horizontally. And then if you take a look at 4, you could see that if you just move him down just a little tiny bit, you could see that the only thing pressure pushing against him has to be atmospheric pressure. So you could convince yourself that 2 also has to be atmospheric. I like to, instead of going 0, let's go to atmospheric here. Let's draw that as 0. So what we're left with is gamma h is equal to 1/2 rho V2 squared. And if you recall that gamma is equal to rho g, right? So you could replace that, maybe, right? V2 is equal to the square root of 2 times gamma h over rho, and you can place this back into there. We end up seeing that V2 is equal to the square root of 2gh. And this is called the, let's see, Torricelli's. Torricelli's, maybe people want to say the C as a ch sound equation. And we've been on the lookout for this. Interesting, the density cancels out, so the velocity here doesn't matter. A special thing that we know, by the way, alternatively, we could take maybe from point 3, which we would say with hydrostatic pressure, which would be gamma times h, right? So that would be, instead of taking it as this term right here, we would replace this P1 or P3, I guess. And notably, there could be a streamline that went like this right there, right? So we can get 2, 4 right there. Remember, we can only use we can really only use Bernoulli's when it's on a streamline, right? On 2 points that are on a streamline, and here, like we saw with 1 and 2, that's the streamline that represents. But we wouldn't really say that 3 goes to 2 on a streamline. Now, numerically, it might work out, but that's only because 2 and 4 share a lot of the same things right there. So just be aware. We want to try to make sure that we're staying within the boundaries we're allowed to. One thing we want to keep in mind is what we're really dealing with here is we had potential energy here, and it turned into kinetic energy there. Or we could also talk about it in terms of head, right? We introduced the idea of head recently. So this was like elevation head, and it turned into velocity head, right? 2 different kinds of head. Another thing we should learn about maybe, is something called the Vena contracta. Now, if the shape of the outlet, like as it is right up here, is like a nice smooth transition, that helps with the hydrodynamics. Just as you probably already know about hydrodynamics, right? So it's nice to have like smooth transitions. It helps generate those streamlines, right? But if you have like a sharp corner right here, we have something called the Vena contracta effect. And what that essentially does is it's going to make like a virtual diameter, right? So it starts out at this diameter, and it contracts down to, it has a virtual diameter. You could probably picture this happening, right? You kind of like visualize that happening. And to account for that, that might be because of the geometry of this piece, right? And it's probably more of a generalization, right? It depends on like the depth of the water or whatever above there. We want to have a significant amount. And you notice this is going horizontally, so we might think of it maybe better suited this way, because we know that it's going to kind of pour out as it's coming down. But this is sort of maybe an averaged type of thing where we can have a coefficient. And so if we know the area between here, we can just multiply, and this is going to be something that's going to be smaller than 1. So some fraction, some like 0.7 or something. And you would just multiply the area between here to get what the actual area is going to be. And we would apply that, I think I have these pages in the wrong order, but that's okay. Here we go. We would apply some of this with confined flows, which we already been using a little bit, but let's go ahead and take a look here. We also have some units that I want to use, right? I want to, take a look at some unit conversions with this page, and then we'll be done with this video. So we know that the volume, right, that would be swept when we have right here, between there and there, is going to be the cross-sectional area times the displacement right there. So that area times the amount of displacement is going to equal the volume. And so therefore the time rate change of that, so the volume flow rate, this could be cubic feet per second or cubic meters per second or whatever, as we're going to see in a minute. Gallons per minute, gallons per hour, liters per second, liters per minute, liters per hour, something along those lines. We would take the time rate change of that, because the area would be staying the same. So that's the same thing as the area times the velocity. So if you've seen that before and you weren't comfortable with it, that's the idea. That the area times the velocity is equal to that volumetric flow rate. And sometimes people use Q. Just be aware. I don't like using Q because that's a heat transfer, very much often used in heat transfer. So I wanted to try to avoid it. And notice right here, and importantly, we know that the conservation of mass, right, of something coming in and out, the mass flow, is going to be density times volumetric, right? And if that density is the same, right here, we could say that that's because it's incompressible. So this is incompressible continuity is implied by having V1, V in equal to V out, right? And then that's because we just said about here, that's where we get the A1 times V1 is equal to A2 times V2. So you might have seen that, and I think maybe we ran across this, but it's a good reminder that we have this confined flow. And using this idea, this incompressible continuity, using that in conjunction with Bernoulli helps us solve a lot of problems, right? Like we could go back to this one right here, and if we know the area right there, and we know the velocity, now we just found what the flow rate is going to be. And if we have the density, we'd have the mass flow. Something we should, numbers worth memorizing. I know that's, they're just an internet a click away, or go to the online conversion factor thing. It's good to memorize some of these. Well, just to kind of visualize what a cubic feet is when it comes to a liquid, and we're familiar with a gallon, like a gallon of milk or whatever. So it's about almost 7.5 gallons for every cubic foot. So you could picture like a 1 foot. That should be a foot. Yeah, that says 1 foot. 1 foot by 1 foot by 1 foot. You can picture a box that's 1 foot on every side. It's kind of hard to imagine that would fit in there, but you could trust me that it does. That you could get 7.5 jugs of milk inside a 1 foot by 1 foot. 1 foot by 1 foot, whatever. Well, see, it really is kind of hard to imagine, right? So that you try to picture that, right? That you get a 1 foot by 1 foot by 1 foot box that you could get 7.5 gallons of milk in there, but you can. Another conversion that you might want to remember is 1 meter, 1 cubic meter, right? So we got 1 cubic meter. You can actually get, if it's a meter on every side, 1 meter by 1 meter by 1 meter, you can actually get into there 1,000 liters. So 1 cubic meter equals 1,000 liters. So, but maybe you could picture 2 liter of Pepsi or something, or your favorite beverage, whatever. And you could picture, like a 2 liter jug that you could put all of those in there. I think what these are useful for is that when you go to flow rates, like one that's very common is a gallon per minute, right? So you could picture how many gallons are operating in a minute of time. You can think of it, it's harder to picture what a cubic foot is per second, but you could picture what maybe how many gallons per minute are coming out of something like me. Picture like it. You want to know how fast your basement's filling up with flood water, right? So you would want, or how fast the pump can pump it out. You want to know for gallons per minute, you can kind of get a sense, or maybe gallons per hour that you would want. So the gallons per minute and gallons per hour are a very common dimension to be used, and it's quite useful. The website I go to often is the online conversion right here. So onlineconversion.com, and go to these different volume flow rates right here. And so you could, prove to yourself that one cubic foot is equal to, how many gallons that is, or go the other way around, right? Notice that they have UK gallons and US dry gallons, right? So we could, why do we have that's going to make a liar out of me. Where's the UK? Is 6.24 gallons. There you go. There you go. U.S. liquid, 7.48. So there you go. So it proved it. I was about to go nuts right there. Couldn't remember that thing. And you go to cubic meter, and you find how many gallons that is. But you go to a liter right there, and you can see it's 1,000 liters. So anyway, that's a useful website if you haven't been using this one already. But getting familiar with different units is important, and when we're talking about volume flow rate, this is an important thing to look at. So let us go back to this and other things. So here you go. Here's the our book, Sengel, getting the Torricelli equation right there. The Vena contracta, spraying water up in the air. Here's another one we'll see. And here's the problem we'll do in the next video.